Hi, I thought I'd make a quick video to answer your questions. The first one you have is which form do you use? I'm just pulling up these answers here. The one I'm showing you is the line drawing. There's really not a preference. I think it may help you to realize that I'm just going to draw right on here. When you have a carbon atom, it can bond to 4 other elements. And that might make sense to you already at this point, but uh, that's why we do all these different methods for drawing it, because you can either show all the carbons and then show all the branched hydrogens coming off of them, or you can just eliminate the carbons altogether, and sometimes that's easier. Most people don't even draw the hydrogens. Um, but so if you're trying to, you really shouldn't have to keep track of more than 3 or 4 carbons. These are just meant to give you some practice um, learning how carbons connect. So sorry, that's maybe not a great answer, but kind of whatever. You really need to be in a position where you can just recognize if there's single bonds or double bonds, and just more of a basic level what the structure is. Your second question is, how do I know if or when there's a double bond? When you give a quite like C5H10, how do you know there's a double bond there? Well, if you put 5 carbons together, let me just kind of write right over this. You go 5 carbons together like this, and they're all going to be connected with, if you connect them all with single bonds, normally you would put the extra potential branches around it, and then I'd put a hydrogen on each one of those. I'm not going to do every one, but you can get the idea really fast. Like, so we'd put a hydrogen on every single one of those, but I'm not going to do that. If you look at it like this, though, with 5, you can see that you can actually count these if you want. See, there'd be a hydrogen here. I'm going to have to just do it quick. So hydrogen, hydrogen, hydrogen. See, all the way around, there'd be hydrogens all around in here, and that's what this is C5H12. You can count. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. See, so there's 12 possible hydrogens. So the thing is that carbon can sometimes bond with itself, and when it does, it will let go of the hydrogens in a sense, and then form a double bond. So what that might look like is that in the very end here, if we got rid of this hydrogen here, now this, here, let's get rid of that too. This carbon is now, it only has 3, and so it will form another bond. Actually, here, let's do that. It'll just form another, because it needs 4, like every carbon needs 4. So what it'll do is it'll just form a double bond between itself and the nearest hydrogen. But now we've lost a hydrogen, and now I'm down to 11 hydrogens, right? Because I had 12 and I just got rid of 1. So if you're going to go C5H10, the only way you can do that is you get rid of 2 hydrogens. Now we could get rid of them in a number of different places, but I'm just going to take that one out at the end and put another bond like this. Now this isn't the only possible configuration, but what you have to see from this is the only way you can get 10 hydrogens is if you form some double bonds. And they could be formed right here, or we could try and do something in the middle if you really wanted to. The point is, those you made double bonds. And that was kind of actually your next question, which was, how do you know if it's saturated or unsaturated? So saturated just means there's no more hydrogens that you can put in there, or there's no more molecules that can bond to it. And that's what's happening up in here. If you look at that, or even in the first hydrocarbon that we did, it's saturated in the sense that you can't take any more. It's kind of like, I think of water when I think of saturated. If you have a saturated towel, it's like it can't take any more water. Well, a saturated hydrocarbon can't take any more hydrogens. But anything that has double bonds, those double bonds could potentially be broken, and we could, we could hook ourselves up with, like I'm just trying to draw one right here. We could hook ourselves back up with another hydrogen if I broke that bond. So anytime there's double or triple bonds, which is what happened when you get to C5H8, you had the only way you could do that is actually, well, wait, we didn't make a triple bond there. We just made more double bonds. So you can keep making double bonds, and ultimately, I don't even think there was a triple bond in that one. But if you have triple bonds, those can be broken too. Your fourth question. Yes, it shows circular after the chemical formula. What does that mean? So let me get down here. See what happens here when you start connecting carbons in a chain, or in a chain. So there'd be a carbon here, 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 and here, but they will actually form bonds with each other, and they form this nice symmetrical hexagon. And because the reigning rule is that carbon needs to be bonded to 4 things at any given time, so there needs to be 4 bonds coming off of every carbon. But we can account for that if we make double bonds on the inside of the ring as shown. Okay, so you can see there's double bonds in there. The thing is that these double bonds actually, they do represent electrons, and the electrons actually can kind of they can go around from carbon to carbon to carbon, and they can kind of shift from one carbon to the next and stay stable, and that's what we call a benzene ring, or just benzene. Oops, and let's put that backwards. Another term for that is an aromatic ring. And the point is just they're really stable. It takes a really high temperature to break them down, whereas a normal hydrocarbon can break pretty easily. These, when they're in that configuration, they're actually really stable. So that's why they're a bit harmful in the environment, because they don't just readily disappear. But that's all you need to know about that. You're not going to necessarily need to draw a whole bunch of those. You just get that right. So this here is the question we're looking at right here. There, I think we got it now. So yeah, the prop-1-ene, that refers to where the double bond is. But the 2 is telling you what carbon the methyl group is on. And we always number the smallest numbers, right? So we start with number 1, 1, 2, and 3 from right to left in this case. But the 2 just means that's where the methyl group is. It's off of carbon number 2. So anyway, sorry that took so long. I hope that's a little bit helpful. I'll follow up again a bit later, and definitely feel free to ask questions. I love it when students actually list them specifically, so that way I can address them as specific as I can. So hopefully that's helpful.